So here we're going to look at the very basics of mass spectrometry. Not all the details you need to know, but a little bit about how it works and how you get a spectrum, right? So inject a molecule, magic happens, computer gives you a spectrum, got to read it, right? We can do better than that. We want to understand what's going on in there, and that'll help understand what the spectrum means and really be able to make sense out of mass spectrometry. For one, notice not spectroscopy because we are not absorbing light and looking at an absorbance spectrum like we would think of for UV or IR. But we do get a spectrum, we do get a result of the molecule hitting a detector and such. So just kind of define terms. So what's going to happen in a mass spectrometry is starting with some molecule. Of course, it can be a mixture, but we can detect molecules. I just drew a simple example of butane. Those molecules within the mass spectrometer get ionized to a molecular ion. So basically, you haven't lost any atoms, you haven't broken any bonds yet, you've just stripped away one electron. So you take away one electron, you have a radical, but it's also going to be a cation. So you call that a radical cation. Because think about it, lose one electron, you're going to have an imbalance of protons and electrons. So written with these brackets here just to kind of imply, yes, there's a plus charge, yes, there's a radical. We're not being specific, however, about what the position of those are, like where the charges are. And within the device, you're going to get fragments. So the molecule will quite literally break into pieces, into separate, smaller parts, right? Sometimes before they get detected. So I'm using the big M to represent the whole molecule, M plus radical here for the ionized version of the whole molecule, and a little m for a fragment. Right, so here's my really ridiculously oversimplified mass spectrometer. Better pictures in your textbook, no doubt. But essentially, the sample has to get in there, so the sample's injected. Right, usually heated and under vacuum to help keep things in the gas phase so they don't condense. And don't end up sticking to any parts within the machine. Right, so essentially we're passing this molecule through the device. And the first and most important thing that happens to that molecule is it gets hit with a beam of electrons. All right, and that might sound a little weird. Think lightning bolt or a small electric charge. And what we're looking at here is that's what's causing the molecule to ionize. Right, so if everything's working well, we've taken an electron off that molecule, and then it's still intact per se, but now it's a radical. So it still maintains all of its mass. Of course, an electron does have mass, but very small. Right? At this point, we're passing this molecule through. We've ionized it. And then it can fragment, right? So you've hit it with a ton of energy. You've put it in an unstable state, right? It's a radical, it's a cation. It can break apart from there, and so then it can fragment. Basically, you're breaking bonds, blowing it apart into a bunch of different pieces. Right, so in this case, you can get a variety of fragments. Right? But not every single molecule will fragment. In a lot of cases, the complete molecule will also survive here as well. Right, so our fragments with charge, and we can talk more about fragments and fragmentation and reading spectrum in another video. This is kind of the basics. Are still being passed through the device and they get accelerated and pass through a magnetic field. Here's my magnetic field. And basically what's happening there is all those little pieces of molecule are separated by their charge to size ratio, and only the positively charged molecules are really going to interact and be sent through. So essentially they're separated by weight. So our pieces can fly through and hit the detector and cause a signal to happen that can be detected and then sent along to the computer. But the different sizes of those fragments, right? So this is one fragment, this is a heavier fragment, this may be the entire molecule that are separated. And the more abundant those fragments are, the bigger the signal you get. So this is essentially turned into your mass spectrum. So if this hits 500 times, 1,000 times, and 250 times, right, you get proportionate signals to how many fragments you have. So that's part of the really useful piece of mass spectrometry is you can use it for detecting molecules, and you'll get a readout and being able to look at masses of all those fragments, but each particular molecule will fragment differently, and all the different fragments you get and the relative abundances of those signals can help us detect what the eventual molecule is going to be. And it works a little bit like a molecular fingerprint, and relatedly can be used to detect those molecules by comparing it to known spectrum. Mass spectrometry, for that reason, is used a lot in things like drug testing and forensics, because you can detect molecules with only very, very small amounts, and they each give distinctive spectrum patterns that are really helpful in figuring out what you've got.